This is video 96 in our series on tensor calculus. In this video, we'll introduce the idea of the parallel transport. This is a technique for comparing one vector to another by transporting it parallel to itself along a curve from one point to another. I expect that when you were first introduced to vectors, you were told that if you wanted to compare a vector in one location to that of another location, what you do is just drag it from one point to the other. So we'd simply grab the tail of this vector, drag it along some path up to the other location, keeping the vector pointed in the same direction the whole time. And so when we did this, we could say that this vector is equal to this vector. All right, well, for our Cartesian coordinates, the analysis of this is really pretty simple. Since the basis vectors are constants, that means that both of these vectors in these two locations will have the same vector components. They'll have the same x and y components in both locations. Well, what happens though if we're dealing with a curvilinear coordinate system, such as plane polar coordinates? Now, of course, we can do the same thing. It's the same space, so we could take a vector and drag it from one point to the other, but this time things are a little bit more complicated. Remember that the basis vectors at this point are not the same as they are right here. So that means that even though these two vectors are equal, they're the same, their vector components will not be the same because the basis vectors have changed. So how do we deal with something like this? When we say that we're dragging this vector along a path, what we're really saying is we're defining a vector field. There's a vector associated with every point along our curve at a position lambda. And our condition for this vector field is that all of the vectors are going to be parallel to each other all along the curve. In other words, if we treat the vector, we'll call it vector t, as a function of lambda, then we insist that it remain constant the whole way, which means that its derivative of our vector t with respect to lambda, and we're treating t as a function of lambda, this derivative has got to be equal to 0 at every point along the curve. Okay, well, let's break this down using the chain rule. We've done this many times before. We'll say that this is equal to ds beta with respect to lambda, and then the partial of our vector t with respect to s beta. So this is just the chain rule. But now the partial derivative of our vector t with respect to the coordinate value is what we've analyzed to be the covariant derivative. We did this, I believe, back in video number 28. So this is going to be equal to d s beta d lambda times the covariant derivative with respect to beta of t alpha times our basis vector s alpha. All right, so what we've got is this portion right here is the same as this because that's the way we analyzed the covariant derivative back in video number 28. Well, if all of this seems very familiar, it should, because everything we've done here is exactly what we did in video number 41 when we were dealing with trajectories. We did the same kind of analysis and wound up defining a new operator called the intrinsic derivative. So we'd have this kind of expression, d lambda times s alpha. So rather than go through that whole thing again, I just refer you back to video number 41 where we defined the intrinsic or the total or the absolute derivative. And this is the way we analyzed it back in that video. So for this process, what we're saying is that all along this curve, we need this intrinsic derivative to be equal to 0. And that process will be known as a parallel transport. Now, back in video 41, we made the point that our new operation here, this intrinsic derivative, is a measure of how the vector or the tensor is changing as we move along the curve parameterized by lambda. Well, what we have here is just a special application of that tool, and it is that in order for a parallel transport to take place, the condition is that this intrinsic derivative has to be equal to 0. The basis vector is not equal to 0, so it's this term that has to be 0 to satisfy the conditions for a parallel transport. So I'll remind you of the various forms that we derived in video 41 for the intrinsic derivative. Remember, we said that the intrinsic derivative can be expressed in either of these two ways, whichever is more appropriate depending on the context of the problem. Well, let's look at this form right here just a minute. If we're dealing with Cartesian coordinates or affine coordinates, the Christoffel symbol is going to be equal to 0, which means that the condition breaks down to simply this. The derivative of our vector components with respect to lambda are 0, which means that our vector components are constant throughout the process. Well, of course, we already knew that for an affine coordinate system. But this expression generalizes the result for curvilinear coordinates as well. The thing that's equal to 0 is the combination of these two terms. The vector components are changing as we go along the curve, and that's represented by this term. But the basis vectors are changing as we move along the curve, and that's taken care of with this expression, and combined together the result is 0. That tells us that the vector itself is not changing as we transport it from point A to point B. Now there's one other form that's quite useful. Because all of this is equal to 0, we can take this portion, move it to the other side of the equation, and reverse the sign of it, and then we can get rid of d lambda here and turn this into a differential expression. And it's going to look like this. The differential of our vector component would be equal to the negative of the Christoffel symbol times the vector itself times this vector. Now this vector is the differential form of this vector, and remember we said this is a vector that is tangent to the curve. So this expression is valid as long as du beta here is tangent to the curve. Now this form is quite useful for analyzing the change in our vector component T alpha as we move in the direction defined by vector u beta. Okay, all of that's pretty straightforward and is pretty easy to understand, at least where flat surfaces are concerned. But what about curved surfaces? Well, let me get rid of this picture and I'll put this one up and we can talk about that. Now, the whole purpose of the parallel transport is to provide us with a tool that allows us to compare a vector at one point in our manifold to a vector at some other point in the manifold. But where a curved surface is concerned, we're generally only interested in comparing vectors that lie in the tangent plane with one another. So that presents us with a problem, because if we were to take a vector that lies in the tangent plane here and truly parallel transport it to this location, then we'd find that because the surface is curved, that this comparison, dragging this vector, would introduce a normal component down here. And we don't want to do that. What we really want to do is to parallel transport the vector as best we can while simultaneously restricting it to the tangent plane throughout the entire process. So think of it this way. We're moving along this line, and as we turn right or left, we have to change the angle of the vector relative to the line where right or left is concerned, and we do so keeping it parallel to itself in a right or left fashion until we arrive at this point. And we simply ignore any effect that the curvature in the normal direction may have. So what that means is that we're going to use exactly the same definitions that we have down here for the parallel transport on a curved surface, just understanding that these equations relate to vectors that lie only in the tangent plane. So by using these definitions on a curved surface, we are in effect doing the best we can to parallel transport the vector, given the restriction that the vector must always lie in the tangent plane. Well, all this will make a lot more sense later on when we have a chance to do a demo. For now, let's move on and take a look at a couple of the properties of the parallel transport. Here I've applied the product rule to taking the covariant derivative of this contraction right here. So we'd first take the covariant derivative of T alpha times V alpha, then the covariant derivative of V alpha times T alpha. So now what I'm going to do is to multiply through by the derivative of S beta with respect to lambda throughout the entire expression. Now at the same time, I'm going to flip-flop these indexes. I'll raise this one while I lower this one. Well, this part of the expression right here is our parallel transport for T alpha, and that'll be equal to 0. This is the parallel transport for our vector V alpha, and it's also equal to 0. And of course that means that adding the two terms together, the whole expression has got to be equal to 0. Now that in turn means that this side is equal to 0, and if that's the case, then the covariant derivative of this expression right here is equal to 0, meaning that the object itself is a constant. In other words, we can say this, that the contraction of T alpha and V alpha is a constant, and that's just the vector component form of a dot product. And that means that our vector T dotted with vector V is a constant. Now, what this means is if we parallel transport two vectors at the same time along the same curve, the dot product between those two vectors will remain constant throughout the whole process. And that property is known as metric compatibility. Now, of course, since this property is generally true, it would also be true that the dot product of t with itself is a constant. And the dot product of t with itself is just the magnitude of vector t squared. So what this tells us is that throughout the transport process, the magnitude of our vector is going to remain constant. It may shift from the left to the right as we transport it along the curve, but its magnitude is going to remain fixed. And of course that's true of all vectors, so the magnitude of t and v is going to remain constant. And therefore, if these are constant and the dot product is constant, then the angle between vectors t and v has to remain constant throughout. So the angular relationship between any vectors that are transported together will remain the same throughout the transport process. They may turn left or right, but they'll turn left or right together and remain at the same angle throughout the whole process. All right, let's move on. Next, let's consider a special case of the parallel transport. Suppose we have a vector t that is tangent to the curve and remains tangent to the curve throughout the entire parallel transport process. Let's see if we can determine what that tells us about the type curve we're dealing with. Well, because of the metric compatibility property, we know that the magnitude of t is going to remain constant throughout the whole process. And since it's always tangent to the curve, we can represent it this way. We can say that our vector t is equal to some constant c times the unit tangent vector s hat. Well, s hat itself is equal to the derivative of our position vector r with respect to the arc length, ds. That in turn can be expanded out using the chain rule. So this is c times ds alpha ds times the partial derivative of our position vector with respect to s alpha. Now, remember s and s alpha are not the same thing. S is the arc length of the curve, s alpha is the coordinate value for our surface. Okay, well that in turn can be written this way. C times d lambda ds times ds alpha d lambda times our basis vector S alpha. All I've done here is to replace this factor with its equivalent using the chain rule involving lambda, and of course this factor is nothing but our basis vector S alpha. Well, to make our life easier, we're going to choose a value for our parameter to be an affine parameter. And remember what that means. Lambda, if it's an affine parameter, is going to be equal to some constant times the arc length plus another constant. Well, that in turn means that d lambda ds is simply equal to a. And that lets us write our expression this way. C a times ds alpha d lambda times our basis vector S alpha. Well, expressed in this form, it's very easy to see that this factor right here is our vector component, T alpha. So what we're going to do now is to substitute this expression into our expression for the parallel transport. So we'll bring up the expression for the parallel transport and simply substitute this in place of T alpha. And of course I had to use index omega here to match omega in this term. Well, the constants c and a exist in both terms, so we can divide that out of the expression and simplify to give us our final form. Of course, by now you recognize this as our expression for a geodesic. So what we can say is this. Whenever we transport a tangent vector along a geodesic, it will remain tangent throughout the entire process. And because of the metric compatibility property, we can also say that a vector which is not tangent will transport at a fixed angle relative to the tangent, like this. Now all this makes perfect sense. As we move along a geodesic, we are, by definition, turning neither to the right nor to the left. Therefore, the angular relationship with any vectors being transported will not change. All this leads to an alternate definition for a geodesic. We can say that a geodesic is a curve generated when we parallel transport a vector in its own direction. Okay, with that, let's wrap up the video with a recap. The expressions you see here are equivalent forms for what we defined as the parallel transport. We can employ any one of these relationships depending on the nature and context of the situation. They all mean the same thing. Note that this is the intrinsic derivative that we developed in video 41. Well, when vector T alpha here satisfies these conditions, it will move along a path defined by a parameter lambda in such a way that it remains parallel to itself while continuing to lie in the tangent plane. We simply ignore any curvature effect in the direction of the normal. The parallel transport is thus a tool that allows us to make comparisons between vectors that lie at two different points in the manifold. Well, there's yet a fourth form that is useful in analyzing the incremental change of our vector T alpha as it is being transported in the direction of vector du beta. Well, the metronomic compatibility property tells us that the dot product between two vectors being transported together will remain constant. This in turn means that the angle between them will remain constant and that the magnitude of any individual vector will remain constant. We also showed that any tangent vector transported along a geodesic will remain tangent throughout the process. This, combined with the metric compatibility property, tells us that any vector transported along a geodesic will maintain a fixed angular relationship with the tangent of the curve. And finally, we pointed out that these results lead to an alternate definition for a geodesic. We can say that a geodesic is a path generated when a vector is parallel transported in its own direction. In the next video, we'll demonstrate these concepts by means of a specific example.